Now I'd like to do a more elaborate example that shows you a lot of the things that we've just been discussing. So to summarize, the story of this example is there's an airplane that flies from a base to point A, and that flight is 280 kilometers in length, and the direction of the flight is 20 degrees north of east. And then the plane flies on to point B. That second leg is a 190 kilometer flight, and the direction of it is 30 degrees west of north. And the question is, find the distance and the direction from the base to point B. In other words, if you were just going to fly straight from the base to point B, which way would you need to go and how far? So in pretty much any problem, I strongly recommend that you make a sketch I'm going to let the x and y axes coincide with the east, west, north, south directions. The base is at the origin, and the first flight, which was in a direction 20 degrees north of east, would look something like this. Here is the point A. I'm going to call this vector P, the displacement during the first flight, and the direction angle of the vector P is theta P. That's just 20 degrees, because the angle was given as 20 degrees north of east. That's counterclockwise from the plus x direction. The second flight was in the direction 30 degrees west of north. North would be straight up. I need to go 30 degrees west of there, which is further counterclockwise. So roughly like so. I'm going to call that vector Q, the displacement in the second flight. And the direction angle of the vector Q should be measured from the positive x direction, which means it should be measured from a line like this. We need to find the angle here, theta Q, for our calculations. Now we were told the Q points 30 degrees west of north, so it's 120 degrees counterclockwise from east, or from the plus x direction. Theta Q will be 120 degrees. To find the distance and the direction from the base to point B, which would be right here, I just need to find the magnitude and direction of this vector. This vector is the sum of the vector P and the vector Q, because the arrangement of my arrows, heads and tails, is just like we discussed for vector addition of vector P plus vector Q. I'm going to call this sum vector R. R equals P plus Q. And I just need to find the magnitude and direction of R. We're going to use components to find the sum of the vectors P and Q. First, let me tabulate the information that we have about P and Q. The magnitude of P is 280 kilometers. The direction angle of P is 20 degrees. The magnitude of Q is 190 kilometers. The direction angle of Q, as we just discussed, is 120 degrees. Now I need to find the components of P and the components of Q in order to add those vectors together. And because we have the direction angles expressed in terms of an angle from the plus x axis, we can use our standard formula for finding the x and y components of vectors. The x component of P is the magnitude of P times the cosine of the direction angle. Using the values given here above, I find 263.1 kilometers for the x component. The y component of P is equal to the magnitude of the vector times the sine of theta P, and I find 95.8 kilometers. It's not a bad idea to take a look at your sketch to see if those numbers make sense. 263 in the horizontal direction, 95.8 in the vertical direction seems plausible. The x and y components of the vector Q are found in a similar way. Q cosine of theta Q would give us the x component. I find minus 95.0 kilometers. The minus sign came from taking the cosine of 120 degrees. The y component is Q sine of theta Q, and I find 164.5 kilometers. A quick look at the sketch would show that these are plausible and reasonable sounding also. Now let's add the two vectors together. R is equal to P plus Q. So the x component of R is equal to the x component of P plus the x component of Q. Using the values we just found for the x components, I get 168.1 kilometers. Similarly, the y component of R is equal to Py plus Qy, and I find 260.3 kilometers. A quick look at the sketch shows that those are reasonable values also for the vector R. We need to find the magnitude and direction of R. The magnitude is equal to the square root of Rx squared plus Ry squared, because R is a vector in the xy plane. And I find 310 kilometers. This is the first answer to the original question, and I'm rounding the answer to 3 sig figs because my inputs have 3 sig figs. To find the direction of the vector R, notice that the tangent of theta R is equal to the y component divided by the x component, which is 1.548. So the direction angle theta R is the inverse tangent of 1.548. The x component of the vector R is positive, so there's no need to add 180 degrees to get the vector direction into the correct quadrant. It will already come out in the correct quadrant. When I use my calculator to find the inverse tangent, I get 57.1 degrees. And that's a reasonable direction for the vector R. That's the other answer to the problem. The problem is finished. But I'd like to do an additional calculation as a further example. We already know the direction of the vector Q because it was given to us. but I want to illustrate finding the direction of vector q from its components, qx and qy. The tangent of theta q is equal to qy over qx, which is equal to minus 1.732. The direction angle theta q is not simply the inverse tangent of that value, because the x component of the vector q is negative. In fact, it was minus 95.0 kilometers. So to find the direction angle of the vector q, I need to take the inverse tangent of minus 1.732 and add 180 degrees. The inverse tangent comes out to be minus 60 degrees on the calculator. So the final answer is minus 60 plus 180 equals 120 degrees, which is actually the direction of vector q that we put into our calculation.